Hello class, welcome to this video on the 5.1 review. So let's go ahead and get started. So there are three types of problem sets here, three types of problems that we want to make sure that we address. So we'll go ahead and start. First one here, first problem set has to do with interpreting probability and things like that. So let's look at the first one here. It says if Lucretia tunes into her favorite radio station at a randomly selected time, there is a 0.2 probability that a commercial will be playing. Explain what this probability means. So when you're interpreting probability or explaining it, you have to be explaining it using the law of large numbers, right? So you're trying to explain what it means. It's over many, many repetitions, okay? So just like in this sample example, what does it mean to have a 0.25 chance of developing cystic fibrosis? Well, if you have to do this over a very large number random sample, okay, probability is predictable in the long run. Okay, so in this example, this is saying that, okay, so if she tunes into her favorite radio station at a large number of times, right? So but randomly, okay. So for part A, if she tunes, or let's say if she randomly tunes in to her favorite station a very large number of times, okay, I'm gonna go ahead and make sure I write it. Okay, so here we go. So very large number of times, then, okay, so if you do something, if you do a very large random sample of something, then the percentage of times that it'll, that in this case a commercial will be playing will approach 20%, okay? Or something like that, okay? So there will be a commercial playing about, so you want to basically do large number of times, random, and about, or roughly, or approximately, or approaching 20% of the time, or of these times, okay. All right, when you do this, you want to be very specific, right, when you're trying to answer these questions. So part B, if Lucretia tunes into this station at 5 randomly selected times, will there be exactly one time when a commercial is playing? Explain your answer. Well, 1/5 is 20%, and it says a 20% probability, right? So you would expect that there would be one station that has commercial play, or one time where it has a commercial playing if you randomly select 5 times, right? That's what's expected. But is that what's going to happen? Well, the answer is probably not, okay? So it's probably not going to happen. And the answer is probably not, right? Because remember that probability is predictable in the long run, but it's not. These things are predictable in the long run, but they're not predictable in the short run, right? So anything could happen. It could be 2 or even none, right? So so ideally, what we want to say is that we would expect 1 out of 5 commercials, but it's not guaranteed. because probability happens in many repetitions. Okay, so yeah, that's the main idea. So if you say something like that. So number 2, Pedro drives the same route to work on Monday through Friday. His route includes one traffic light. According to the local traffic department, there's a 55% probability that the light will be red. Explain what this probability means. Okay, so remember, again, very large number of times, right? And random. So that means if you select a very large random sample of times during the day and look at the lights, about 55% of the time the light will be red. So you can say so I'm using the word about, very large number of times, going through the same light at different times, things like that. 55% of the time the light will be red. Okay. All right. So there you go. So that's what it means. So that's number 2. So anything similar to that. Number 3, a local weather forecast says there's a 20% chance of rain tomorrow. Explain what this probability means. Okay, so it says tomorrow. So there's the key there. Okay, so tomorrow. So that means that very large random sample, but you have to have days like tomorrow. Okay, so with the same conditions. So if you have days like tomorrow with the same conditions, the same wind speed, the same humidity, the same temperature, this and that. If you have those same conditions, then and you repeat that multiple times, right? You have many days like that randomly. Then about 20% of those days it will rain. Okay, so that's basically what it's saying. All right, so in other words, so if you select a very large random sample of days with conditions like tomorrow, with conditions like tomorrow, there will be some rain about 20% of the days, of those days. So of the days. Okay, so again, very large, random. You're talking about specifically what you're talking about, days like tomorrow, and then about, and then the percentage. Okay, all right, so that's your kind of guideline to go by. Okay, problem set number 2 is talking about the law of averages and misconceptions with the law of averages. So this one says, okay, there's 7 girls in a row. So the doctor says that the probability that there's going to be a boy is going to be is going to increase. It's going to be much more likely to get a boy. And we know that this is wrong because remember that probability, the way the chance works, right? In this case is that, it's still 50% chance of getting a boy or girl. If you're talking about in terms of probability, you got a 50% chance of boy, 50% chance of girl, right? If you have no idea of what the conditions are, it's going to be 50% each. So, and that's not going to change just because you have 7 girls, right? So so that's something that we want to keep in mind. So no matter, even if you have a streak or something like that, it's not going to change the probability. A very good professional baseball player gets a hit about 35% of the time. After the player failed to hit safely in 6 straight at-bats, a TV commentator said he is due for a hit by the law of averages. Explain why the commentator is wrong. Okay, so basically here they remember the law of large numbers is that if you have multiple repetitions, right? You need multiple repetitions in order for the proportion to approach the probability, right? So you can say this, that they misapplied the law of large numbers to a small number of repetitions. You could say that, but the most important thing is that basically you say, okay, why was it wrong? Is that the probability stays the same. So that's what we want. Okay, so even after the player failed to hit safely, in 6 straight at-bats, the probability of getting the next hit is still the same, 35%. Okay, so it's not like it's going to change just because he's got a streak, right? Probability is not it's not affected by the streak. If it's completely independent, then the probability should be the same. Okay, ideally. All right, so number 2, a college basketball player makes about 75% of her free throws. In one game, the player makes her first 5 free throw attempts. When the player steps to the free throw line for a 6th attempt, a radio announcer says that she is due for a miss. Explain why the announcer is wrong. So they're using the law of averages there again, right? So again, if she has about 75% rate, then it should maintain around 75%. Okay, it's not like it's going to change. So the probability stays the same of making the next free throw, even if she's got a streak. Okay, so even after player makes her first 5 free throws or free throw attempts, she will continue to have the same probability, right? The same 75% chance of making the next free throw. Okay, and that's really what it is. But it's really what it boils down to. Imagine rolling a die 12 times and recording the result of each roll. Which of the following outcomes is more likely? And then they give you something. They give you 2 different outcomes, and they want you to explain. Okay. Now remember, this has to do with the same concept, even though it's worded a little differently. Even though it looks like a different question, it's really the same idea. And the idea is, it doesn't matter if you have a streak or, like in this case, like order or disorder in your results. It's still going to be the same probability of occurring, right? The next set of outcomes is just as likely as the next. So even though, if you look at this one, even though this is in order, right, forwards and then backwards, and then this looks kind of scrambled, it's not going to change the probability of getting either one. Okay, the probability is going to remain the same. So in fact, in this example, the 2 outcomes are equally likely. So in this case, any sequence of 12 die, any 12 die rolls that looks exactly like that has the same chances of occurring. Okay, so any possibilities or slash sequences of rolling a die 12 times will be equally likely. Since the chance of getting the chance of getting a particular number is 1 out of 6, right? So is the same. So the chance of getting any particular number on a die is 1 out of 6. It's going to be the same no matter what, right? So getting the next number is still going to be the same outcome, the same odds. And so if I do this multiple times, it's not going to change the probability of 1/6, right? And so we wouldn't expect that if I rolled it 12 times with that same probability for each time, that these two separate outcomes would be different, the probability. Okay, they actually are the same, and we're going to calculate that probability in a future lesson. But for now, just know that these outcomes are equally likely according to theoretical probability. All right, so we have here the next problem set is on simulations. So in this example, we need to come up with steps for how we're going to run the simulation. And then calculate the probability, and then actually draw a conclusion. Okay, so that's what we're doing. All right, so number 1, a professional tennis player claims to get 90% of her second serves in play. In a recent match, the player missed 5 of her 20 second serves. Is this a surprising result that the player's claim is true? Assume that the player has a 0.10 probability of missing each second serve. Okay, so we want to carry out a simulation to estimate the probability that she would miss 5 or more of her 20 second serves. Describe how to use a random number generator to perform 1 repetition of the simulation. So it says she claims to get 90% of her second serves in play. So and then it says that she missed 5 of her 20 second serves. So we want to see if that 90% is true, right? So what we're going to do is we're going to say, okay, we have 10. We're going to do 10 numbers, and 1 through 9 means that the serve is that she gets the serve, and then the 10, it means that the serve is out. Okay, so that means that she misses, I guess, the serve. Okay, so we're gonna say let 1 through 9, number 1 through 9, equal makes the serve, and 10 equal misses the serve. Okay, and then what we're gonna do is we're gonna record the number of missed. So we're gonna before we record we're gonna use RNG, right? So we're gonna use a random number generator to simulate selecting a random sample of 20 serves. So we're going to record, let me write this out better. Record the number of missed serves. So record the number of missed serves in a sample of 20. Okay, so basically we're going to generate 20 numbers 20 random numbers. So generate 20 random numbers between 1 and 10. So we're going to generate 20 random numbers between 1 and 10. And we're going to record the number of missed serves that we got and the number of tens, okay? And that's our simulate. That's going to be the simulation, okay? And then we do this multiple times, and then for our experiment. So the dot plot displays a number of second serves missed by the player out of 20 in 100 simulated matches. So they did these steps 100 times, and they got these dots. So if the dot at 6 right here represents that out of 20 second serves, right, she missed 6 of them. Okay, so in one trial. So it's saying that in one repetition of the simulation, the player missed 6 out of 20 second serves. All right, and that takes care of that. Use the results to estimate the probability that the player will miss 5 or more of her 20 second serves in a match. Okay, so 5 or more, that's this. So that's 2, 4, if we count those, that's 7. Okay, and remember, they did this 100 times, so there's actually 100 dots here. Okay, so what's the probability that the player would miss 5 or more shots? So the probability is equal to 7 out of 100, which is 7%. So 7% of the time, she would miss 5 or more of her 20-second serves by chance, if what her claim is true, that she's a 90%, that she does it 90% of the time. Okay, if that claim is true. Now, based on the actual result of 5 missed second serves and your answer to part C, is there convincing evidence that the player's claim is false? And then explain your reasoning. And now remember that the cutoff for determining whether we have convincing evidence or not is 5%. So here we got 7%, which is greater than 5%. So if it's 7%, that means it's likely that she would have missed 5 second serves by chance. Which means that if that's likely to occur by chance, that means that we don't have enough evidence that the player was lying. The player was lying about the 90%. Okay, because this is if she missed it in 7% of the time, that means she made it 93% of the time, or that means 93% of the time she didn't miss 5 or more serves, right? And so we just don't have enough evidence to say that the 90% number is incorrect. Okay, so as long as it's greater than 5%, we don't have enough evidence. Okay, so I'm going to say it is somewhat unlikely, which means that we got a probability of 0.07, which is greater than 0.05. A tennis player who makes 90% of her second serves will miss 5 or more of 20 serves by chance alone. So there is not convincing evidence that player's claim is false. Okay, and this is the hardest part for students to to do is this conclusion part, right? So it's the idea of, do we have enough evidence versus do we not have enough evidence? Okay. All right, so number 2, about 7% of men in the United States have some form of red-green color blindness. Suppose we randomly select one U.S. adult male at a time until we find one who is red-green colorblind. Should we be surprised if it takes us 20 or more men before we get to that point, before we find somebody that's red-green colorblind? Describe how you would design a simulation to help answer this question. Okay, so because it's a 7% chance, right? We want to make sure that when we do 7% means 7 out of 100, right? And so what we could do, okay, is that we could say, okay, let's randomly generate numbers between 1 and 100, okay? And then let 1 through 7 be adult males that have red-green color blindness. RG, I'm just going to say RG blindness, okay? And then and let 8 to 100 be those without, okay? So let 1 to 7 equal equals RG blindness, and 8 to 100 equals not RG. So I'm going to say RG blind or not RG blind, okay? So what we're going to do is use RNG to simulate randomly selecting an adult male. Generate 100 or generate. So how many numbers? So we're going to continue to generate numbers. So we're going to generate random numbers between 1 and 100. Okay, and continuing to generate them until a number between 1 and 7 is selected, or is obtained. And then we're saying, okay, how many numbers did it take to get to that number between 1 and 7? Okay, record the number of adult males selected. Okay, all right, and that's how we're going to do it. So in 24 out of 100 repetitions of the simulation, it took 20 or more randomly selected men to find one who is red-green colorblind. Based on this result, how would you answer the question of interest? I explain your reasoning. Okay, so so the question of interest here. Okay, so they found that the probability is 24%. Okay, so they said the probability is 24%, basically 24 out of 100. Okay, so 24% of the time of the simulations of the repetitions, it took 20 or more people to find one who is red-green colorblind. So so really that is greater than 5%, right? That's likely for that to happen. Okay, so it is somewhat likely so I'm going to say it's somewhat likely to need 20 or to sample 20 or more adult males before getting someone that's red, green, colorblind. Okay, so to find one who is red, green, colorblind. In this case, 24% is greater than 5%, right? And so that means we don't have enough evidence to basically, we don't have enough evidence to say that. Yeah, so we don't have enough evidence to say that it would not take 20 or more men, right? We have no evidence to disprove this thing, that it would not take 20 or more men before you find somebody, okay? So therefore, we really shouldn't be surprised. This is likely to happen, okay? It's somewhat likely to, so let me just read the questions. Somewhat likely to sample 20 or more adults to find one who is red, green, colorblind. So we shouldn't be surprised at this result, right? We shouldn't be surprised if it takes 20 or more men. Okay, so hopefully that made sense. That was a little easier. There's less work for that one than the other ones, but for these two. In a certain archery competition, each player continues to shoot until he or she misses the center of the target twice. Quincy is one of the archers in this competition. Based on past experience, she has a 0.60 probability of hitting the center of the target on each shot. Should we be surprised if Quincy stays in the competition for at least 10 shots? All right, so let's see. Okay, so remember, she's got to miss 2 shots, right? It says here that they have to miss twice. And remember, she's 60% rate of making it, of hitting the target, the center. So that means, okay, so six, that's the same thing as 6 out of 10, right? So we're going to generate random numbers from between 1 and 10. And then 1 through 6 is going to represent, missing or making it or hitting at the center, and then 7 to 10 missing the center. Okay, so let 1 through 6 equals hit the center, and 7 to 10 equals miss the center. Use a random number generator, RNG, to generate, and we're gonna continue to generate random integers. Okay, so here to generate integers between 1 and 10 until, so we keep doing this until we get a number between 7 and 10 twice. Okay, this means that, okay, she missed twice, so she's out, right? So we keep doing this. Okay, and then what we're going to do is we keep record the number of shots that it took to get to that point. Okay, so then record the number of shots she took. All right, and then we'll see. We'll test her claim to see if she claims she has 60.60 probability of hitting the center. We'll see if that's true, or if we have enough evidence to disprove that. So in 3 out of 100 repetitions of the simulation, Quincy stayed in the competition for at least 10 shots. So she stayed in the competition for at least 10 shots 3 out of 100 times. That is interesting, okay? So now 3 out of 100, that's that probability of that's 3%, right? Which is less than 5%, less than or equal to 5%. Okay, so that means that if she if it's less than or equal to 5%, that means we have enough evidence to disprove, right? So that's the idea, okay? So So since the probability is, I said, did they want us to probability? Yeah, based on this result, how will you answer? Okay, so we just got to answer it. So based on the simulation, it is unlikely for a 60% shooter to remain in the competition for at least 10 shots. Therefore, we should be surprised. So we have enough evidence to reject her claim, or disprove her claim, or dispute. We'll say dispute her claim. And we should be surprised if she remains for at least 10 shots. Okay, and that's that should do it for that part. And then and that's it, guys. So that should do it for the lesson review. I hope you found this useful and informative, and as usual, I'll see you in the next one.